Another example concerning diagonalizability. Okay, this one's mercifully not as long as some of the other ones. The question is, determine whether this matrix is diagonalizable. They give us a matrix. Anything catch your eye about this matrix? It's got a lot of zeros in it. Actually, this is an upper triangular matrix. And that's going to be a world of help when we go through and solve this. All right, worst come to worst, I can find all the eigenvalues, find the corresponding eigenvectors, make sure they're linearly independent. That could take a while. I think this one's not quite that involved, though. Conceptually, there's some ideas along those lines. Okay, so let's find eigenvalues first. For eigenvalues, we consider the characteristic polynomial. Consider the determinant of a minus lambda I, set that equal to 0. There's the characteristic equation. We've usually done it one piece at a time. But for us, that would give us, we want 0 to equal the determinant of a minus lambda I. That'd be -1 minus lambda. 0's underneath. 4, 5 minus lambda. 0's underneath. 2, 3, -5 minus lambda, 0's underneath, -7, 6, 1, and 11 minus lambda. Okay, we need the determinant of this matrix. This is an upper triangular matrix as well. So it's easy to take the determinants of upper triangular matrices. Remember, it was a product of the diagonal elements. We had an example, I'll quote here in a second, that told us that. You ought to believe it. You think, well, I'd expand along the first column because of all the zeros. Then I'd look at a minor matrix. Well, I'd expand it along the first column as well because of all the zeros. There's even another 0 down there. So what we'll get then is the product of the diagonal elements of this matrix, because since this matrix, A minus lambda I, is upper triangular, so the determinant is the product of the diagonal entries. Who said that? It's page 255, example 4. And we've mentioned this before. So that's what justifies this instead of doing a bunch of expansions. All right. Oh, then it's easy to find the eigenvalues in this one. So the eigenvalues will set that characteristic polynomial equal to 0. We'll solve the characteristic equation. The eigenvalues are, okay, let's see, we'll list them in order, as we always have. Would be what makes this term, or this term, or this term, or this term 0. This term is 0 when lambda is -1. Lambda is 5, lambda is -5, and lambda is 11. So we'll take lambda 1. What was the least of those? It was -5. We'll take lambda 1 to be -5, lambda 2 to be -1. We've developed this habit of listing the eigenvalues in increasing order, increasing greatness, greater than, less than, as they're arranged along the real line. Who's next? 5, and then 11. Okay, so there's the eigenvalues. Excellent. That wasn't too bad. We've been through a lot worse in finding eigenvalues. What was the question? Is the matrix diagonalizable? Well, there's the eigenvalues. Recognize anything with the eigenvalues? They're all different. And we said at some point, if the eigenvalues are different, then the corresponding eigenvectors are linearly independent and the matrix is diagonalizable. That was theorem 5.3. And so notice the eigenvalues are distinct. They're all different. There was 4 of them. We started with a 4 by 4 matrix. we should get 4 eigenvalues. If you let me count multiplicity and use complex numbers, we'll get 4 of them. Here we've got 4 distinct real eigenvalues, so we're in pretty good shape. The eigenvalues are distinct, so by was theorem 5.3. That one had a little name. Its little name was independence of eigenvectors. It said, in part, that eigenvectors associated with different eigenvalues are linearly independent. We've got 4 distinct eigenvalues. So if we were to find, we don't have to, that's what makes this a bit easier. If we were to find all the eigenvectors associated with this and with this and with this and with this, then we'd have ourselves, if we chose representatives, we'd have 4 linearly independent eigenvectors if we chose representatives of those classes. And we'd put those into a matrix C. The columns would be linearly independent. Matrix C would be invertible. That's exactly what diagonalizable means. And more directly, theorem 5.3 told us that matrix A, satisfying these properties, is diagonalizable. So here's one requires a little bit of theoretical knowledge. And not a whole bunch of computations. Mercifully, it's an upper triangular matrix, and finding the eigenvalues was easy.